Okay, thank you very much for being here. I'm from the physical biology group in the University of Frankfurt. So this talk is not absolutely complete, so I'm not going to make any calculations because I was not sure whether the computer that I'm using here would be sufficient. But it all comes from a working lab book, which I'm using all the time for this. It simply illustrates a few aspects of the development process. I should add maybe that I've been developing microscopes for, well, since 1983, for the past 30 years or so. And I've been using Mathematica more or less ever since it has become available. And I assume that essentially all the papers that we've written, and there are about 240 or so, they all include a little bit of Mathematica somewhere. And particularly the development part contains a lot. And basically all is, of course, based somehow on physics, and you will see this here during the talk. So what I will talk about is I will briefly talk about how we evaluate some of the images. As I said before, the underlying notebook is really the basic part. I'll talk about the basic layout of the instruments. I'll talk a little bit about patterns. You will see why. And I'll also present some images of latex beads and yeast cells that we use usually to test these kind of systems. So where is this talk? In our scientific circle, which was just basically introduced also by Bina in the talk. So we're somewhere, the colors here are on the real side, but the color here is totally different than it is here. So this is our cycle. So we have a scientific challenge, and then we work through method development, experiments, data acquisition, and so on, to modeling. Then we reconsider what we want to do, and then we basically start again by redefining the scientific challenge. And I am somewhere in this talk, somewhere between here, between methods development and data processing. So that's essentially in this part here. So we're not really talking about a scientific challenge in the sense that we want to answer a biological question, but we're really interested here in instrument development. And what we are building for this purpose is what we call Coherent structured illumination light sheet-based fluorescence microscopes. And the basic idea of, most of you are probably aware of microscopes that contain maybe one lens or two lenses, and then you use maybe in fluorescence microscopy, you use a single lens, such as this one here, for the illumination and the detection of the specimen. And we are using, in light sheet-based fluorescence microscopy, at least two microscope objective lenses. We use one lens for the illumination, and it creates a light sheet. That's what you see here by looking into the detection lens. And then we use a second lens for the detection of the light. And in our coherent setup, we go another step forward. We use two lenses for the illumination, and we have two counter-propagating beams here. And these two counter-propagating beams, they are coherent, and therefore they can interfere. And in this way, we create a pattern which we illuminate the specimen, and then we observe this pattern at an angle of 90 degrees. And the nice feature of the instrument that we've built over the last 2 years is that we can change the orientation of the pattern, and it might become a little bit clearer during the talk why this is of importance. So we have a pattern here which contains stripes along this axis, and if you go along this direction, as you can see, the pattern is slightly rotated. And these are some real patterns. And as you can see, the frequency here of the pattern changes. So here we have a period of 314 nanometers, goes in this case up to 614 nanometers. And the other important part is that I said is that the pattern, the orientation here of the pattern can change a little bit. So it can change from up here, down here, and you can see we have here different degrees, angles, minus 49 to here plus 23 degrees. The slight variations that you see here, they are basically here due to the fact that we have a kind of moire pattern here in this whole setup. And here are some real images. I will start with this because I don't want to generate any suspense whether this works or not, but it actually does. So here are some patterns that we create of different latex beads here along different directions. And this is the traditional view that you would see. So that is a fairly high resolution image that you would get. But if we now use this coherent structured illumination, you see we get a much finer distribution, much smaller latex speed. So we really get the resolution improvement that we are looking forward to. And we can also do this with some real specimens. These were previously latex beads, and here we have some yeast cells, and you see that is the ordinary view here with our microscope of such a yeast cell, and that would be a view that we would get if we have an improved resolution. And that is just a transmission picture to make sure that we really see a yeast cell.
What's the size of the white bar?
The bar here in this case, good question. Usually this is a PowerPoint talk and I just copied this, I have to admit, and this probably got lost. I can tell you later. I'm really sorry that I'm not able to answer this question right now. Now, where does this come from? Well, this actually is somehow related to moiré patterns. And here's a nice picture. So essentially what you see here is an overlay of this pattern here. So it's just basically a set of holes in a hexagonal fashion. And if you have two of those on top of each other, then you can somehow see an enlarged view here of those patterns, of those holes. Yeah? So we cannot identify that here in the image, but in this case, under certain conditions, certain angle and so on, we could actually see this. So in a certain sense, this acts as a telescope or something like this, so because it really gives you an improved resolution. So how do we take advantage of this? And well, you can just phrase, let's say, a single plane wave here. I don't want to make this too big, but not too small. So here we can just identify a single plane wave, and if we just calculate here the magnitude of this, so the product of the function and its conjugate, then of course we see it's just a constant, nothing really special. But when we have counter-propagating waves, so we have exactly the same function up here, but now we change the direction here by minus x, and then calculate the magnitude. In this case, I have to say also divided by 2. Then you see we have a pattern, a sinusoidal pattern. And the nice feature for us is that this sinusoidal pattern, or the frequency of this sinusoidal pattern, only depends on the wavelength, essentially. I'm not going to explain this in great detail, but that is important for us. And it is important because it actually means that that the resolution does not depend anymore on the numerical aperture of the system, as I'll indicate briefly at the very end. Now, if we look at this in a little bit more detail, just perform a full simplify of this function here, then we already see this is a kind of pattern. That's exactly what we see. So we have 0.5 times 1, so that's the constant part, which is then modulated here with a cosine of 2x. Now we can analyze this a little bit further. I'm just simplifying this. So here we have an image, doesn't really matter, I of 0, 1 plus cosine, and here we have our pattern again. If I perform a trig expand, then we already notice, of course, that we have two components here. We have a cosine and we have a sine function. And if I now show this in exponential form, with a trig to exp here in this case, then we actually already see that we really have different components here in the frequency space. And if I perform a Fourier transform of this, then I actually see, okay, here I have a Dirac delta in one position, and I have two further Dirac delta functions, which are shifted now by this function k0. So which is, as you can see, directly related to the pattern that I actually use. So that actually means, let's have another look at this very carefully. So this I of 0 is actually our image. And you can see if I generate these patterns, I actually get 3 of those images. So I get an image at the regular frequency of the object, but then I get actually 2 further images, which are shifted, in this case, by k0 to either side in the frequency space. The question is, can I retrieve this information? And the question is, how many of those patterns do I actually require? And a simple, it's a kind of idea how you can address this is, if we now generate, let's say, 3 of those patterns and just phase shift them and generate here these 3 patterns, which are here now in red, green, and blue, and then add those patterns, which I do down here. So here I just generate those patterns, different phases you see here, 0, pi thirds, 2 pi thirds, and then here I generate the same functions and just add them. Then you see we come up with an even function again. So that is an indication, I would say, that if we have 3 of those patterns, we can actually we get all the information that we have about the object. Now, the big issue here is that we have this function here, which is exactly the one that I derived from before. I just copied it into here. So again, we have this k component, we have this k0 minus k component, and we have this k0 plus k component. But as I said, we now have 3 phases, and that actually means we have 3 of those functions. And if I just phrase this differently, and I've done this down here just to make life simple, I get essentially 3 different images. I, of course, always have the same image, but then I have this matrix here. Yeah? And this matrix is now multiplied with these 3 currently unknown functions, so the currently unknown images. So I have the image, which I said before is exactly in the position where I usually record it if I don't have a pattern, and then I have 2 extra components whose location in frequency space is now determined by the frequency of the pattern with which I modulate the image. Now let's have another look. What does this really look like, and what is the consequence? So here's my test image, and we used to call this a single or selective plane illumination microscope, and that's why I usually call everything spimage processing. And this object here, which is really pixel exact, but again, due to moiraying, you don't really see this here. So originally, all these 3 lines have exactly the same thickness, and also down here they have exactly the same thickness. So this is an image that I calculated to make absolutely sure that everything is pixel exact, but as you know, there's a mismatch between the resolution that we have here and the resolution with which we display it. So this is the kind of object that I'm looking at, and I really have lines along different directions. I have points here. I have a square, a circle, and then I have these objects here where the intersecting part is always of importance. And then I write a text in here, spimage processing, because that is something that we as humans easily recognize. And now what I have to do is essentially I have to generate 3 images by multiplying them with these kind of patterns that I show here on the left-hand side, on the right-hand side. And these are the images that I then get. And what I usually do is I'm welcome to get all the code if you want, but I usually generate these kind of frames here. So I'm really doing this, I'm already thinking about the kind of talk that I might give, usually in PowerPoint, and also for documentation purposes. So I really take actually great care in writing everything down and making sure that I get reasonable comparisons. But essentially these are nothing else but large grid calls. So what do I get? So first of all, we have our original data here. And then I convolve the original data with my kernel, which gives me the isotropic convolution. And then I deconvolve this, and this is the kind of best image that I can actually get. So I can never get this, but I will always get something that is close to this. Now I can multiply this with different phases. Here, phase 0, phase 1, and phase 2. And the real trick here is that you see that some of the objects appear and disappear, which is, of course, part of an improved resolution. Improving the resolution does not mean essentially that you see more, but you see less. But you know where this little information comes from. And that is exactly what we're doing here. And I can also deconvolve it, and that is the kind of information. These images here on the right-hand side are the ones that I'm later going to use for the image processing. Okay, now the real part is to perform the matrix inversion, because, of course, as you saw before, the information that I'm really interested in was here on the right-hand side. Okay, so that is something that is relatively simple. Here's the whole calculation. but I will skip through it. It doesn't really matter. It's something you can do quite easily. But in the end, we really have the inverted matrix. I'm also performing here tests, as you can see, because I'm not quite sure whether it's exactly the same, and so on. And then I get various different versions here of my matrix, a numerical one, and then also symbolic ones, and so on. But this is usually quite easy, and that has caused a lot of confusion, I have to say, in the literature, because, of course, it was miscalculated every now and then. Now, what happens? Here now I'm performing the reconstruction. So here are the images that I recalled. These are the 3 images that you saw before, and then I'm also running some test images. Then I'm just multiplying these 3 images with the components here, 1, 2, 3 of the matrix, of the inverted matrix, of the inversion, and then I'm just adding them. Now, let's first have a look at the spectra. So here you see the power spectrum, which I calculate here, of the actual image, or the one that should not be shifted, and here are the 2 shifted images, and you see there are slight asymmetries. And I also shift them here. I'm also changing here the scale a little bit. You see here I'm multiplying the image with 1,000, here with 100. I'm just scaling it because the dynamic range in these Fourier transforms is usually very high, and here I'm just basically interested in some rough features. And these are really the 3 images. These are the 3 pieces of information. So the original one is shifted to the right, and the other data set is shifted to the left. And then I can combine the information, and now you can see that in frequency space, the information is improved because the thickness is now much larger. Okay, and here's just a summary once again of this. And now we can have a look how the improvement occurs. So again, we have here our original data. These are just some convolutions. Here's the isotropic convolution, so that is the kind of goal that we would like to get. And here you see the sum of the images, and here you see the deconvolved part, and you can already notice that you can read the text much, much better. And I can also combine it in different manners, but we'll leave this out, and I'm also using line plots to make absolutely sure that it's really quantitative. But of course, this was only along a single direction, and essentially I'm doing the same calculations. I now move not only along one direction, but I'm moving along another direction, orthogonal to it. So there's a data set with 2 directions, and I'm just summarizing this. So we can reconstruct it. We do exactly the same calculations, a little bit more complicated because we have more images now, but it's still just an addition. You can see that I now get improvements in frequency space not only laterally, horizontally, but also vertically. I combine the information. Here you see that the frequency space is now heavily improved. And this is the kind of image that I already get. And again, and if I just compare that again, here, let's just take this line here. You see the deconvolved one. You see the sum along x, sum along y. And here you see the sum along x and y, and also the deconvolved one. And the text is now really very well readable. So with a relatively simple trick, you actually improve the resolution quite dramatically. And we can go even a step further. And that is really important because with this kind of system that we've generated, we can really generate different frequencies. And we're doing, okay, I'm in the last few minutes, but I don't need much more. And now we're doing it with 2 different frequencies in the whole system. And let me just show this one below. So that is the single view, low frequency. This is the high frequency part. And the problem with when you use very high frequencies is that you generate these zeros here. And these zeros always mean that, as you can see, you get these kind of lines here on the side, so kind of double images. But if you now combine these 2 different frequencies and make sure that the space is filled in frequency space, then you truly get images such as this one. As you can see, the lines are now really well recovered. The text is perfectly readable, and you really get the perfect information. In practice, we actually go even further. We not only take 2 directions, but we take not only 4, but actually 6 to 8 directions. Okay, and let me just conclude by showing you the actual data. So let me just mention one problem that we have here. So what I showed you were ideal cases, no noise. But in practice, of course, we have noise problems, as usual. So here is of the latex beads, 2 directions, or several directions actually. So this is the actual image. Here we see the shifted image to the left and the shifted image to the right. And this peak here that you see here, maybe, I hope, that is actually gives us an indication of where the K0 actually is. And you see it here on the left, and you see it here on the right. Here you see it in the top left, and here in the bottom right, so we can actually identify them. But if we really look at this, and these in circles here show the calculated locations, you notice there's a slight difference here. And that is, of course, where Mathematica comes in again, because we know in principle where it is, and now we can look de facto where it actually is, and then we take this information also into account in the actual reconstruction. Okay, and let me just conclude. Well, this is the original information without an improved resolution, and this is the process data, and now in this case we're looking at mitochondria in yeast. We can really see the mitochondria. The resolution improvement is somewhere between 2.6 and 4, depending on the resolution, which is very dramatic, because you have to take this to the power of 3 in 3 dimensions. So what I did is we use one tool. Actually, everything's done in Mathematica. I should also say that this goes by next to, so Boré, with whom I do this, he performs all the calculations in C, and we're just making I really programmed this completely on my own, just to make absolutely sure that whatever he does and publishes is absolutely correct. I've been doing that over many years now, and maybe it's a little bit different, but basically it's everything is exactly the same. And I really want to thank my colleagues, Alexander, who will give a talk after lunch, Bina, who gave a talk this morning, and Sabine, who unluckily cannot be here. And of course, I also want to thank the funding partners. And thank you very much for your attention.